I, Satish Soni, welcome you all for technical lecture from NCTS. This will be a series of 3 lectures on basic metallurgy and inoculation. The first lecture today is titled as Basic Gray Iron Metallurgy, and we have Mr. Madhav Athavale to take us through this. Mr. Athavale has completed Master of Engineering program from Indian Institute of Science, Bangalore, specializing in foundry sciences way back in 1980. He worked with Foseco India Limited in the technology and marketing area for 33 years before retiring as head of technology and marketing. As he is always ready to guide and share his knowledge, he has presented papers at Institute of Indian Foundrymen seminars as well as in seminars of other industry associations. He continues to work as consultant to technical training as well as marketing. I now request him to take over. Over to you, sir.
I sincerely thank Institute of Indian Foundrymen and NCTS here in Pune for allowing me this opportunity to make this presentation. It has been a while since I retired, it's almost 7 years. However, I have been keeping in touch with the foundry industry, and teaching and sharing experiences is something which I have enjoyed throughout my career in Foseco, as well as post-retirement occasional work which I do in terms of training with people. Let us first have a look at the material selection for a component, say like a casting of some shape. Then we will look at what is cast iron. Then we will look at solidification of gray cast iron and factors that affect the microstructure. Then we will have a look at effect of various elements on the behavior of gray cast iron microstructure and properties. Factors, there are other factors which affect the strength of gray cast iron, so we'll have a look at them. Then, having understood this, we will then go over to how do you go about controlling the microstructure and hence the properties so that we meet the casting buyer's specifications. And then I'll walk you through quickly a few applications of gray cast iron. So here we go. Material selection for a component. Now you can ask a question, what a casting buyer wants. And I would say that the criteria for buying the castings is the buyer wants dimensions and properties at a particular cost. Now dimensions can be internal or external, which are governed by the mold and core that you use, while the properties are largely driven by the kind of microstructure, and cost of procurement obviously depends on the production efficiency of the plant which is producing it. So the efficiencies in the entire casting production process. Let's look at an example, an engine block. Now, an engine block, if you see here, it is subjected to a variety of stresses during its working life. Various parts. So certain areas, there's an internal combustion engine block. So you would need strength at room temperatures, you would need strength at high temperatures, static strength, you will also require dynamic strength, because an engine block has to withstand the stresses which come from cyclical combustion pressure. Then there is a crankshaft rotating in the engine block. So the thermal expansion of the engine block has to be accommodated. You need strength and hardness at room temperatures for handling of the casting, as well as to ensure good machinability and as well as for the assembly. You need good fatigue strength for the material because, as I said earlier, cyclic tensile stresses and over a wide temperature range. The block material has to have good thermal conductivity. For example, in modern engine blocks, you'll find that the crankshaft bearings reach a temperature of 150 degrees centigrade, while in between the bore, interbore regions of the casting section may see temperatures up to 200 degrees centigrade. Now, there are many materials which can compete for this in today's world. Grey cast iron has been and still is one of the most popular materials of construction. Aluminum and its alloys after due heat treatment is another option. Some very light castings, even magnesium alloys would be used. Also, our engine blocks, people use compacted graphite iron. But today, our focus is going to be on grey cast iron. Let's explore quickly what are the typical dimensional and property requirements for an engine block. So plus minus 1 mm in general dimensions, in wall thickness, you have plus minus 0.5 mm, machining allowance of 2.5 to 3 mm. I've taken typical numbers. And when it comes to strength, tensile strength, greater than or equal to 250 newtons per mm square for this typical specification. And it also specifies from what part of the casting the test sample has to be taken. And in case of sections which are between 7.5 to 30 mm, the strength requirements are in the range of 210 to 250 newtons per millimeter square. And hardness is 190 to 240 BH. I have said BHS. S stands for hardened steel ball indenter. Now, if these mechanical properties are to be achieved, mechanical as well as thermal properties, then the material specification, assuming that we have chosen material of construction as gray iron, is given here. So they are specifying chromium should be less than so much, sulfur should be less than so much, etc. And importantly, they say that carbon, silicon, manganese are not binding as long as they guarantee to achieve the mechanical and structural properties as specified. So the emphasis is on getting the right microstructure so that you achieve the desired mechanical properties. The typical microstructural characteristics are, I have just underlined and put in red the important points. Laminar pearlitic matrix in all sections, presence of ferrite in quantities less than 5%, graphite type A number 4, and then scattered low quantities of type B and D are accepted, where substantial thickness variation occurs. And then last but not the least, traces of cementite or free carbide less than 1%. Why I have highlighted and put these words in red is, these are the things which we are going to discuss as we go forward in this presentation. Cast iron is a family of alloys, predominantly iron, which is a metal, carbon, which is a non-metal, which is 2 to 4%, and silicon, which is 1 to 3%, which is a transient metal. They are also unique. These alloys, this is very important. They are also unique because of the double eutectic phase diagram, and we will shortly see what I mean by this. Cast iron will also contain manganese, sulfur, phosphorus when it is originating from pig iron as one of the input materials. Alloying elements like chromium, nickel, moly, etc. will be used to produce alloys for getting specific grades for special applications. The challenge for the foundry technologists or metallurgists is how do you manage the structure of the iron, that is the matrix and the shape of the graphite, so that you get the required mechanical properties. That's the trick. So let's look at solidification of cast iron, factors affecting the microstructure. And to understand this, let's look at the phase diagram of iron carbon system and then understand the solidification and the microstructures. Now, what is a phase diagram? Well, a phase diagram is basically a chart. This chart is used to show the conditions at which thermodynamically distinct phases occur. They not only occur, they coexist in equilibrium. What is a phase? Phase is a region or space in which the material has got uniform properties. That's what we mean by phase. Now, a typical phase diagram will have lines of equilibrium or phase boundaries, and these will be shown in the diagram which follows this slide. Now, these are the boundaries which mark the conditions under which multiple phases can coexist at equilibrium, and phase transitions occur along the lines of equilibrium. That means as the metal is cast and it starts solidifying, certain phases appear, and then over a period of time and temperature range, changes will happen into those phases. Here is a typical iron carbon diagram. On y-axis, you will see you have temperature. On the x-axis, we have carbon equivalent, and we'll come to the concept of carbon equivalent shortly. The lines that you see here, the solid lines, these are the phase boundaries. You also see a dotted line, and that dotted line is, we call it as graphite line. I'll go into the details as we go forward. The black lines are for cementite. Now, in this diagram, if you look at, liquid is the first phase. Then on the left-hand side, you see something called austenite, which is a phase of iron. That means a certain amount of carbon is dissolved in iron in the form of austenite, which has got a particular crystal structure, which we'll see in the next slides. Then down below, you will see as the temperature drops, you will also find something called cementite or graphite, which is shown here. This particular line is known as eutectic line. This is a line where at a particular composition like 4.3% carbon equivalent, liquid will get transformed into two solids. So it will be an austenite plus graphite or cementite. Why this or? I'll come to it later. And then as the metal cools through and comes down to say 738 degrees, austenite gets transformed further into ferrite and either graphite or cementite. Now, I have used so many words. I'll add one more thing which is shown here in the diagram. At this eutectic temperature 4.3, which is very crucial in cast iron applications, the compositions which are to the left of this are called as hypoeutectic compositions. So those castings are called as hypoeutectic castings. And compositions to the right, where your carbon equivalent is more than 4.3, they are called as hypereutectic ions. Let's come to this important idea of carbon equivalent. Why the term carbon equivalent is that the other elements which are present in a typical cast iron melt, such as silicon, manganese, sulfur, phosphorus, they have an effect on solubility of carbon in iron. So that particular effect of encouragement of these elements for carbon to come out of the solution is taken cognizance of by defining a carbon equivalent figure, where here, for the sake of simplicity, many people use it as percentage carbon plus percentage silicon by 3. Many times people will also add percentage phosphorus by 3. In fact, if you go into the original thermodynamic equations, you will find effects of manganese, which is slightly negative, sulfur, and few other elements. So once again, remember that the composition of the iron has got a big impact on what microstructure we will get. And what I mean by microstructure is what type of phases are going to be present in a given cross section of the metal. I have already covered silicon reduces solubility of carbon in austenite and promotes what we call as graphitization. Another important point, as you are seeing here, there is carbon can come out in an iron carbon melt either as free form of carbon, which is called as graphite, or it can come out as a combined carbon as an intermetallic compound, cementite. Its formula is Fe3C. And whether the metal will freeze or solidify as per graphite diagram or as per the cementite diagram is affected by number of important parameters. One of them is what is the carbon equivalent of iron. Number two is what is the nucleation level in the molten iron. And third important part is what is the cooling rate. All of these things tend to decide whether graphite will come out of the solution or cementite will come out. Wider the gap, that means if we want to look at it from the point of looking at the effect of these various factors on the position of the dotted lines and position of the solid lines, then I would say wider the gap between the graphite line and cementite line, the higher is the potential for graphitization. Now these two bars indicate generally what is the carbon equivalent range in which typical engineering grade cast irons are used. These are the typical compositions. But theoretically, you can have a composition starting right from 2% carbon equivalent going up to 5% carbon equivalent. And like I said earlier, phases have a big impact on the microstructure and properties. So we will have a look at that as we go forward. Let's have a quick look at crystal structure of various phases. We talked about austenite, ferrite, and cementite. Now, cementite, as I said, has chemical formula of Fe3C. It is an intermetallic compound, and it has got a fixed carbon level of 6.67%. Let's look at austenite. What you see here is a structure which is called as face center cubic. That means here the iron, when it freezes, if you do the X-ray diffraction studies, you will find that the structure is in the form of cube, and the iron atoms are occupying the positions not only at all the corners of the cube, but an atom is also present at the center of each face. And that is why it is called as face-centered cubic structure. When it comes to another phase, ferrite, which is present here down below, and which has very small solubility level of carbon. Ferrite has what we call as body-centered cubic structure. So iron molecules or iron atoms are present at all the corners plus at the center of the cube. So the first one we call as FCC structure. The ferrite we say has got a body-centered cubic structure, and cementite has got little more complex structure, where you can see these green balls here. They are the carbon atoms in, and the blue ones are 12 numbers of iron atoms. So it is orthorhombic structure. Now, instead of cementite, I said, if the conditions are right, you may get graphite coming out of the solution, and graphite has what we call as hexagonal closed packed structure, where each ball here represents an atom of carbon. The carbon is present in the iron. It so to say dissolves in iron structure as an interstitial solution, because at room temperature these are all what is called as solid solutions. So in case of austenite, the carbon tends to get at this position along the edge, while in case of ferrite, again it occupies the place along the edge. Now imagine a lattice structure where you have many such cubes or unit cells of grain. So these are the interstices within the iron structure which get occupied by carbon atoms. It is able to do this filling the gap because the diameter of the carbon atom is much smaller than iron. The law says that for getting an interstitial solid solution, the solute has to have a diameter, solute atom has to have a diameter which is at least 40% less than the solvent atom. In this case, iron is the solvent. Now, what is the significance of this? Austenite, as we saw, has got face-centered cubic structure, and during solidification, three-dimensional dendrites are formed, and then as the temperature drops, it will get transformed into cementite and ferrite, etc. But normally in low alloy cast irons, austenite will not be present at room temperatures. Then comes cementite, which is orthorhombic, as we saw. And the important point is it is extremely hard. the hardness number is greater than 350. In appearance, it is a plate-like structure which is very hard and brittle. It grows as two-dimensional dendrite and it forms because of undercooling. Now, what we mean by undercooling, we will see in the further slides as we move through this presentation. But important to remember, while it gives us hard particles within the matrix, too much of this will cause reduction in the machinability. The tools will tend to get damaged because they are really, really hard particles. Now, graphite, as we saw, has hexagonal closed pack structure and it is very soft. The BHN is only 5. Now, graphite can form from the molten iron by either homogeneous or heterogeneous nucleation, and it affects the mechanical properties, the form and the size in which it comes out has a big impact on the strength properties that we get, as well as the machinability of the component that we have formed. Ferrite, as we saw, has body-centered cubic structure and it is softer than cementite. Hardness level is only 150 to 200, so it is a soft phase. Lowers the tensile strength, but it gives you higher elongation, reduces hardness. It also helps in improving impact properties, but it can make, because it is soft, machining can become a bit sluggish. And the last but not least is the perlite. Perlite is a structure where you have alternate cementite and ferrite plate-like lamella. And so you have one soft phase lamella followed by one hard phase lamella. So it has got a hardness which is intermediate between ferrite and cementite. So generally increases hardness and strength, reduces elongation and impact properties, but improves machinability. Why I'm stressing on this importance is we are finally looking at how to go about achieving the mechanical properties. And to get these mechanical properties, we must ensure that the type and form of graphite, the amount of ferrite, the amount of perlite, and the size and size of perlite is what is going to have a big effect on the mechanical properties that we will achieve. Now, while I have very briefly touched upon how the phases occur in cast iron, I have taken a small portion, that is the cast iron range of this iron carbon diagram which we had seen earlier. Again, temperature on y-axis and carbon equivalent on the x-axis. And then you can see those liquid, and that is graphite eutectic lines, graphite lines and cementite lines, which are shown. At 1153 degrees centigrade, you have your graphite eutectic line. At 1148 degrees centigrade, you have your cementite eutectic line. So, if the cooling conditions of the molten iron are such that it follows the Fe3C type of reaction, then you will get carbon in combined form. I'm repeating myself because it is very important to remember this, because we have to control both these things. While if the solidification progresses as per the solid line, dotted line there, then this sort of a solidification reaction will result in carbon coming out of molten iron in the form of free carbon on the. Now, as the graphitization abilities of the cast iron increase, then the melting point and solidification shrinkage decreases. because as your carbon equivalent increases, as you can see, this particular line, which forms a boundary between liquid and sort of austenite on the left-hand side, this is your liquidus line. So as you can see, that line is dipping. That means the start of solidification line, temperature at which solidification starts is coming down. So melting point and solidification shrinkage. Because this particular gap that we see between liquidus and solidus line also tells you the tendency for formation of shrinkages. The wider the gap, more are the chances of shrinkages. And in iron's case, it could be micro shrinkages, sometimes gross shrinkages. Because your liquidus temperature drops, the fluidity also is higher. The metal is able to flow more freely as the graphitization tendency increases, as more graphite comes out of the solution. And as more graphite comes out of the solution, the ability of vibration absorption increases, thermal conductivity and machinability also increases. So if I have to summarize, we can drive the solidification to reaction we want by using control over chemistry, control over the cooling rates to an extent, because cooling rates is a function of what is your pouring temperature and what is the geometry of the casting and what is the conductivity of your molding material. But casting geometry has got a good impact on cooling rates. Third and very important part, which is level of nucleation which is present in the bath. Now, so if you are able to have a control over these things, then we'll be able to drive the solidification reaction to achieve the desired microstructure and in turn get the desired mechanical properties. Let me take a schematic. Let me take a schematic of cast iron microstructures, and I am considering hypoeutectic alloys. You can see it here on the left-hand side. I have said 2.5 to 4% carbon, which is a big range. Towards the lower carbon side of it, and if you do faster cooling, most of the iron will solidify as white iron, which is carbon coming out in combined form, which is Fe3C, cementite. It is called as white iron because if you fracture it, it is pretty brittle. It will show a shiny white fracture, relatively white iron. If the cooling is happening at a moderate rate, then carbon will come out, and as you are moving towards higher carbon levels compared to what you had on the lower side, then some amount of graphite will come out of the solution as flakes, as you can see, and what you see in the background, or the matrix as we call it, of pearlite, which is alternate lamellae of ferrite and cementite. And if you do the slow cooling and have a carbon which is towards the higher end of the spectrum, then more carbon will come out of the solution. So you will have graphite flakes and a ferritic matrix. In case of white cast iron, which is sometimes, or which some time ago was being used for making malleable iron. So you reheat it, hold it for some 30 plus hours. There are different cycles for this heat treatment. And then if you do the fast cooling, you will get what we call as pearlitic malleable iron. And if you do slow cooling, you will get what we call as ferritic malleable iron. Why malleable? Because this iron will exhibit ductility, unlike the cast iron here. or gray iron. In fact, gray iron is called as gray, as all of you really know, is because the fracture of the iron looks gray. Now, during the heat treatment, this cementite sort of breaks down. I'm using very crude terminology, and carbon diffuses comes out, and it agglomerates in the form of these graphite shapes here. And do it for long enough time, slow cool, and much of the carbon will come out and leaving behind ferritic matrix. That gives you even bigger elongation than what you will get with poor lithium. Now, in the present days, instead of malleable iron, people have started producing what we call as ductile iron, which is an American term, or spheroidal graphite iron, where you take the base iron, deliberately lower the sulfur levels, and do the treatment with magnesium. And when the solidification takes place, the carbon comes out in the form of nodules, as you can see. And when you are doing moderate cooling and carbon equivalent, which is slightly on the lower side, you will get a polytic matrix. While you do the slow cooling, and you will get ferritic ductile iron. Generally, ferritic will have higher ductility, higher elongation compared to polytic, but the strength-wise, it will be shade lower. More about ductile iron at a later date. Now, let's quickly look at the types of graphite flakes in gray iron. This type of a flake, which is uniformly distributed but random orientation, this generally gives you the best properties and typically specified for powertrain components like engine blocks and gearbox housings, etc., etc. Next one is type B flake structure. This appears like rosettes with random orientation of graphite flakes. It occurs often in near eutectic alloys where there is improperly inoculated metal. That means nucleation levels are poor. Because nucleation levels are poor, the graphite nuclei are less, so you will tend to have less number of grains and bigger grains. And the smaller flakes at the center happen because of the undercooling. The third type of structure is C. Now, this occurs in hypereutectic ions. That means you have a carbon equivalent more than 4.3. So the primary phase which comes out of solution will be graphite, because graphite is coming out, can come out at two stages, as in this case, primary phase coming out is graphite, and then as austenite cools down, again you will have ferrite and graphite coming if the right conditions are there. This kind of a structure can sometimes occur if the iron is over inoculated where the carbon equivalent is also high. The primary graphite, by the way, is called as Kish graphite, and it reduces tensile property, very large needle like. Now, type D type of flake structure, this occurs as a result of interdendritic segregation in the rapidly cooled ions. That means the cooling rate has a big impact. It consists of, you see these small ant-like things here, randomly oriented flakes between the austenite dendrites. And type D may lead to higher tensile properties, but heat treatment can become difficult. And the last one is type E flake structure. Here again it is interdendritic graphite, but the flakes are oriented, as you can see. The earlier ones, you had random orientation of interdendritic graphite flakes, while here they are sort of aligned in a particular direction. This tends to happen in ions with low carbon equivalent and again undercooling. Now, this was the type of graphite. Now, let us look at the sizes of graphite in cast iron, and that is what is given by this diagram. If you think back on the specification of the engine block microstructure that we saw, it specified a type of graphite with size 4 flake. A4 it said, which means a flake which is 12 to 25 mm average length at 100 magnification. Now, whether you want A4 or you want A6 or you want A2 is really decided by what are the service conditions of the component and what are the strength levels which are required at critical areas in the casting section. Now, after looking at how the graphite forms and what are the types of flakes that you will see in gray iron, let's look at effect of various elements. Here is a graph which shows percentage of alloying element on the x-axis and change in the carbon solubility, which is expressed as delta percentage C on y-axis. Now, what you will notice is that sulfur, phosphorus, silicon, antimony, copper, and nickel, these elements at different addition levels, and here of course alloying has been taken all the way up to 25% just to show the trends that there is a negative change in the carbon solubility. That means the solubility of the carbon in iron comes down, or in other words, these elements, when they are present in the iron, they will promote or they'll encourage carbon to come out of the solution as graphite. While if you look at the other elements, vanadium, manganese, chromium, molybdenum, these elements have a positive change in the carbon solubility. That means they will promote formation of combined carbon. They will say, okay, carbon, please stay inside the iron matrix, which comes out as cementite. So these are the elements which tend to encourage formation of Fe3C instead of carbon coming out in the free form, which is graphite. See, in case of cast irons, the actual presence of these elements, unless for some alloying purpose higher addition levels are there, will be towards a very low end of the spectrum. I have shown a table of typical compositions for various grades of ions. But I have chosen this graph so that you know the trends are same. Basically, this graph is shown to show you the trends. That means who is pushing out, who is encouraging carbon to come out of the iron, and who are the ones who are holding on that carbon along with iron to form cementite, which is the hard phase. Diagrammatically, on a phase diagram, it can be seen like this, that chromium, vanadium, molybdenum, and manganese, they will reduce the graphitization potential. That means they will push up the cementite line upwards and they will push the graphite line downward. That means the gap between the two will get reduced. So the tendency for formation when the metal is solidifying from say this temperature and you have higher amount of these elements, then there is a good chance that you will land up with carbides in your matrix. There is a good chance that you have cementite and more pearlite coming in. While you have silicon, phosphorus, aluminum, copper, nickel, these are the ones which lift up the graphite line and press down the Fe3C line, cementite line, so they will promote the graphitization. This is a small table which summarizes effect of main elements, important elements, trace elements, and dangerous elements. So as we have discussed, iron, carbon, and silicon, they govern the proportion of graphite in the structure. They govern the structure of the iron matrix also. Now, phosphorus, manganese, sulfur, copper, as we saw, their effect. They have a big influence on matrix of the iron. That means whether pearlite will form or carbides will form. They also help, especially rare earths and sulfur. They will define the shape of the graphite as well. Usually, manganese is used for neutralizing the sulfur because sulfur tends to form low melting phases in iron. So it needs to be taken care, and manganese balances it out. The rule of thumb is the percentage of manganese in your iron should be 1.7 times sulfur plus up to 0.3. That's the number. And people will use this as one of the controlling tools for ensuring that you get good microstructure without problems. Now, I said nickel, moly, bismuth, titanium, vanadium, these are trace elements. So they are really in small quantities, but they can sometimes be useful. It depends on what charge materials you are using. And then there is a group of elements which we call them as dangerous trace elements because they can cause defects in the casting. They can cause abnormal graphite shapes, inclusions, and weaken the casting. I mean, aluminum beyond a particular limit may even give you pinholing, especially when you are using green sand molds. Now, one part of what we saw was effect of individual elements, but since many of them are present, let us look at the effects of composition. So for example, you look at carbon, and carbon is in the range of 2.8 to 3.7. As the carbon increases, the ultimate tensile strength comes down, the hardness comes down, because it promotes coarser graphite, it improves the fluidity of the iron, and increases thermal conductivity. Silicon, as its proportion increases, it promotes graphite because as we saw, it encourages carbon to come out from solution in liquid state and solution in solid state. That means from austenite also carbon will come out more readily. There are many to explain this phenomena, there are other phase diagrams which are available, but I have not covered them in this. Let us keep it simple to the basics. So this will reduce the strength, hardness, but it will also reduce carbides and chills. That means formation of cementite along the edges of the casting. Phosphorus, it forms low melting phases. Iron phosphide will form along the cell boundaries or grain boundaries as we call them. What is a cell we will see in next slides. But it is hard and brittle, and because it is a low melting phase, the metal has what is called a searching tendency. Because it is highly fluid, it can encourage metal penetration into the mold, it can encourage finning in the castings. Carbon equivalent, here I have taken the definition of percentage carbon plus 1/3 silicon plus 1/3 phosphorus. This is an indication of how close an ion composition is near to the eutectic. And from all the discussion that we have earlier, higher the carbon equivalent values, lower will be the tensile strength and hardness, because more graphite will come out of the solution. We have higher amount of graphite coming out. As a result, the strength will be lower. Here is a table which I have taken from the Casting Development Center, which was earlier known as BCI, British Cast Iron Association. And as you can see, for producing different grades, 150, 200, 250, 300, 350, what is the typical composition and range that one has to keep in order to get these grades? This is one of the key parameters for the control. As you can see, as you go towards the higher grades, the carbon equivalent goes down, the sulfur goes down as you go towards 300, 350 grades. Phosphorus also goes down. And for higher grades, you may add molybdenum and copper or nickel. Copper has an added advantage that it tends to refine the pearlite. That means your graphite lamellae will be finer, which strengthens the matrix. Now, let us move towards factors affecting the strength of the gray iron. Here is a graph which I have taken from CDC literature, which talks about tensile strength versus cross-section thickness. And it has been, the lines have been drawn for different grades of ions. The important point that one should notice is that irrespective of what grade you are trying to cast, because finally grades are done on standard test bars, while actual casting will have multiple section thicknesses. So even though, as an example, you are casting a grade 350 iron, because in a higher section thickness, the cooling rates will be slower, the microstructure will tend to be coarser, so the strengths will be lower, as you can see from the graph, as compared to a thinner section. So I have, as an example, I have drawn two vertical red dotted lines there. One is for a sort of 15 millimeters thick plate or thick section, and 75 millimeters thick section. And then you can see across the grades, the strengths are higher when the section thickness is thinner, because grain size, or cell count as we call in case of ions, cast irons, is higher, while as the section thickness increases, the cooling rates become slower, so grains become coarser, so that, or even though apparently you are casting the same grade, the actual strength levels in the sections will be different. So that is one thing that one has to keep in mind. This is another graph again taken from CDC literature. It shows tensile strength versus carbon equivalent in decreasing order here on the x-axis, again for different diameter test pass, which will represent different casting section thicknesses. And as you can see in all the cases, for all these lines, as the carbon equivalent goes down, the strength levels will go up, because thinner the section, faster is going to be the cooling, more finer will be the grain size, and perhaps if the nucleation levels are properly managed, you will have more pearlite into the matrix. So combined effect of the size, cell size, and the type of microstructure will be felt here. So this is effect of composition on tensile strength. Earlier we saw effect of section thickness. Now next relationship is machinability of gray cast irons. This is again taken from CDC. And on the left hand side, sort of equivalent plate thickness as shown, while on the right hand side there is a bar diameter. And again you see, so higher thicknesses at the bottom, lower section thicknesses at the top. So slow cooling to fast cooling. So cooling rate, thickness is also giving you an idea of a cooling rate. And then you have carbon equivalent, which is going down from 5 to 3. And let's look at microstructures. On the left hand side, when you have higher carbon equivalents and higher thicknesses, you will have softer and machinable iron because you have ferrite plus pearlite. And good amount of graphite also would have come out. And coarser graphite perhaps. While as the carbon equivalent goes down, and which are marked as engineering gray ions, here the strength levels will go up. The microstructure will be sort of pearlite, and machinability will be pretty good. While as you go towards the lower side of the carbon equivalent, between 3.3 and 3, as the thickness goes down, that means faster cooling rate, one will land up with chilled or mottled iron, which because cementite is very hard, it will be difficult to machine or unmachine it. So this is the relationship between carbon equivalent, thickness, the type of microstructure, and machining. Now, cast and microstructure control. Having looked at how the solidification happens and what are the various factors which affect the microstructure, we have to use these for deliberately bringing control over the microstructure. Now, when we say we have to manage the microstructure, we have to manage the graphite. That means the amount of graphite and the size and shape of the graphite, and persuade carbon atoms to come out of the solution and not form carbides. Then managing the structure of the ion matrix, that means how much could be the size of the pearlite and size of the ferrite and how much amount of carbides and what is the texture and size of the pearlite. So here we get into carbon equivalents, and we'll see them one by one. And also managing the inclusions, because the inclusions will disrupt the matrix and will cause lowering of the properties. What are the control tools and techniques we have? Now, for graphite type, one important portion is the melt chemistry, as we saw the sort of type of compositions. We saw a table earlier. What kind of composition of the melt is required for producing different grades. So that is one control we have. Nucleation levels, which is charge makeup, as well as inoculation type and technique. I will say a few words about inoculation, but only a few to explain the principle, because inoculation by itself can be a separate presentation. The importance of charge makeup is, see, typically in gray iron, you would have a charge makeup which may contain some amount of pig iron, may or may not. Then foundry returns, steel scrap, various ferroalloys to make up for silicon, etc. And what proportion of these materials you will use and what is their history will decide what I call as base nucleation levels. Normally, pig iron tends to have, even on melting, good amount of nuclei present in the bath. While if you have more of steel charge, steel scrap, and less of pig iron and less of foundry returns, then the nucleation levels can go down, and then you will have to adjust your inoculation type and technique to ensure that you get the right nucleation levels to get the desired microstructure. Cooling rates. See, one factor which will have effect on cooling rate is what is your pouring temperature. Higher the pouring temperature, rest everything in terms of mold side remaining same. Then the higher temperature, because the differentials are larger, will have faster cooling, but bigger impact is of casting geometry. Thinner sections will, because of more rapid heat extraction, will tend to cool faster than the thicker sections. And then this variation in the section thickness also will cause change in the microstructure, and that needs to be sort of countered by bringing in proper nucleation levels. Matrix type is governed by melt chemistry. That means your carbon equivalents, rate of cooling, presence of alloying elements. So again, charge makeup and inoculation type and technique has an impact on the matrix. Chemistry has a big impact on that. And cooling time in the mold also has an impact on melt chemistry, because if you allow longer solidification time, then more carbon can come out from the solution or from austenite or cementite, and more ferrite can form if it is slow cooling, and coarser grains, especially if nucleation level is not balanced. Now, what are the types of control equipments and measures that are used? I think most of you who are working in foundries, they are very familiar with. For chemistry, your spectrometers, or you use CE meters and maybe carbon sulfur apparatus for checking the chemistry of the melt as well as of the casting if you want. Then thermal analysis is another tool which is used to judge the nucleation levels, or even to judge different types of inoculants. If you want to explore which inoculation type and technique is best for producing a given casting, then thermal analysis is a good tool. Another simple test is the wet chill test. Very, very effective. So we will see what that wet chill test is there. As far as pouring temperatures are concerned, I think all of you are familiar, thermocouples on the furnace and ensuring that you don't overheat the metal. These are the kind of things that one needs to do. See, overheating also has a very direct impact on the nucleation levels, because higher the superheat and longer the holding times, lesser will become the nucleation levels. Also, some of the elements may be lost if the holding time is too large. Coming to the casting geometry, not only a single casting geometry and its section thickness variations have impact on cooling rates. The layout of the pattern, see, many times in iron foundries, you would have, if your pattern plate is large enough, you will have multiple number of cavities. And so the total amount of metal being poured in the mold, and how much is the surrounding sand in the mold, because finally the heat is going to get transmitted or conducted through the sand which is surrounding the metal. So metal to sand ratio is very vital. Why it is vital is, if you have too less amount of sand, that means you are putting a lot of castings in a given pattern plate, then it will create problems in multiple ways. One, the cooling would be a problem because you have lesser amount of sand present. The sand can become very hot if your metal to sand ratios, that means the proportion of sand is on a lower side. and that itself creates its own problems. We have already seen this earlier, approximate metal chemistries data from CDC. What I have done is I have put down below one line here which talks about carbon equivalent, and please pardon me for not removing those 4 and 5 digits there beyond decimal. It's from an Excel file. But what you can see is the carbon equivalent goes down as the grade increases, because you will start getting more and more perlite in the matrix. Do good nucleation, and then you will have a finer grain structure, finer graphite. So it will result in higher grades. See, inoculation is a means of controlling the structure and properties of cast iron by minimizing what we call as undercooling. It promotes heterogeneous graphite nucleation by introducing elements that form suitable substrates that will act as nuclei and initiate the desired graphite formation, and it modifies the structure and properties of the casting. In normal practice, people will use, or they were earlier using, graphite, calcium silicide, or ferrosilicon containing elements like aluminum, calcium, barium, strontium, zirconium, which provide the nuclei and which alter the solidification characteristics of the melt. Now, here is what we meant by undercooling. Now, the dotted line here is cooling curve for an uninoculated iron. That means there are less number of nuclei which are present, and the iron cools down much more through, and it crosses a carbide eutectic line and then rises again as the nucleation starts. I mean, this is not only true, the phenomena of undercooling is present in all the metals as they freeze. The basic reason why you get what we call as undercooling is that as the metal starts freezing, in order for the atoms to start getting deposited on the nuclei, that a stable surface, the stable solid surface to form in the liquid, you need some surface energy which is adequate, and that is taken out from, that energy is taken out from the melt. So there is a local level, what we call as undercooling. So you may have a particular temperature which we formally call as either eutectic temperature or melting temperature, but when actual solidification is happening in real life conditions, to ensure that the nuclei are stable, it has to undercool, and that energy is useful for creating the nuclei, stable nuclei. That is why this phenomena of undercooling happens. Now, this particular undercooling, which is shown here by this red arrow, for cast irons, it can mean the difference of whether you will get graphite or you may get cementite. Because the top line there is for graphite eutectic, EG, while the bottom line is for cementite eutectic. When we saw the iron carbon diagram earlier, we had discussed about this. So if the nucleation level in the bath is less, then the undercooling takes place and the temperature may drop below the cementite eutectic line and formation of cementite Fe3C instead of formation of carbon coming out of the solution as a solid will happen. So if you provide adequate number of nuclei through this inoculation, so we are externally adding something into the bath which reduces the necessity for this thermodynamic phenomena called thermodynamics driven phenomena called undercooling to take place, because already a surface is available. So the metal need not go down to that level, and so inoculation helps in reducing the degree of undercooling, thereby ensuring that you don't get carbides don't come out. It also prolongs the formation and growth of graphite, thereby increasing the solidification time as shown by the green arrow. Okay, so that way the effect of inoculation is simple: reduce the undercooling tendency of the ion by providing external nuclei which are the right type, so that the graphite or carbon molecules will deposit on those substrates in the form of graphite rather than getting combined with iron as cement ion. So here is what happens after inoculation, is nucleation plus growth. So you are providing the external nuclei and they start growing by taking out either austenite or carbon. So during solidification, cells of graphite and austenite form in the liquid that this picture shows. And down below you see what we call as eutectic cell, eutectic compositions. You get these graphite and surrounding austenite forming cell, and then these cells will merge to form flake graphite structures in gray iron, while in case of ductile ion, a eutectic cell will be a graphite nodule in the center surrounded by an austenite, we call it. And at room temperatures, we will see this as bullseye structure, as they call it. So here is another diagram. Graphite nuclei has grown, then you have austenite sitting there, growing along with graphite. So a eutectic cell is formed. And here is a scanning electron microscope picture of such graphite flakes, a 3D form. Now, in gray cast irons, of the right composition and adequate level of nucleation and slow cooling, graphite flakes in ferritic matrix will happen, while graphite flakes in pearlitic matrix will happen when the nucleation levels and the chemistry and the cooling rates, or slightly faster cooling rates, okay level of nucleation levels and alloying elements, and overall lower carbon equivalents is what will result in pearlitic matrix. Pearlite is alternate lamellae of cementite ferrite. Now a few words on inoculation and graphite type. Earlier we had seen A, B, C, D, E types of graphite. This is a picture which I pulled out of I think Osego found in his handbook. So for A type of graphite, well nucleated ion, carbon equivalent which is good, slow cooling rates, and well nucleated means degree of undercooling is less. While B type of graphite will form when degree of undercooling is higher, and you get rosettes, so inoculated or undernucleated. While graphite type C can be over inoculated or hypereutectic graphite, while D is again undercooled graphite. Now you have got austenites. You can see the dendrites here and interdendritic liquid as it freezes, randomly oriented small graphite flakes coming out. And type E, as we had discussed earlier. higher degree of undercooling, but oriented graphite fields. This is undesirable. Here is another diagram which is showing fast cooling and slow cooling and different levels of nucleation, and how whether the solidification will occur as white iron, that is cementite, will form, or gray iron will form. Pretty self-explanatory, really. It basically shows us the importance of nucleation. Importance of nucleation both in fast cooling as well as slow cooling bands. And like I said earlier, thin sections cool faster than thick sections. Adequate nucleation necessary to avoid carboids in thin section. Now, I have added a few bullets on. There are situations where you need a particular type of faster cooling needed. You want actually a hard surface. You want cementite on the surface in extreme case, or you want to promote directional solidification. That is when we use chills. Chills mostly get used for directional solidification purposes, so that you take care of feeding of the iron and avoid any shrinkage processes. And some exceptional cases, foundries use what I have called as metallurgical coatings, where they will use the coating on a more specific area of mold and core, where you want faster cooling in very localized areas, and you actually want to have white iron. So these metallurgical coatings can be of tellurium, or they may contain bismuth, or sometimes tin. The severity of kind of cooling decreases. Tellurium gives you highest, followed by bismuth, followed by tin. And really the functioning is pretty simple. These are all elements which have low evaporation points, evaporation temperatures. So as soon as metal comes in contact with a surface which has been coated with any of these, in that localized area, for the purpose of evaporation of these elements, heat will be taken out of the surrounding metal. So the cooling rates will suddenly increase in that local area, and tellurium will invariably, you will land up with cementite, that is carbide on the surface, and very undesirable forms of microstructure behind it. Bismuth gives you densening effect, and sometimes tin will be used in some exceptional cases. I have known of a few cases when tin coatings have been used, where there is a long cooling time resulting in coarser sort of grain structure. So instead of getting A6 type of graphite, you are perhaps getting a coarser type of graphite. So when the cell size goes down because of this faster cooling in specific areas, so these are to be used as medicinal coating for special purposes only, not for general purpose. The point here I was making was that controlling the cooling rate to get the desired microstructure in specific part of the casting is something which is done through this. Chilling tendency assessment of wedge test, which is a very, very simple and well-known test. This again, I have taken a picture from CDC data sheets. It's also there in Precision Foundament's handbook. It's a triangular shaped wedge, and T, the thickness that you see of the white iron which has been formed, Fe3C which has been formed, is called as the chill width, or if you go height-wise, it will be called as chill depth. So the wedge is made in a mold prepared from silicate or resin bonded sands. After pouring, it must be allowed to cool in the mold to dull red heat. That is very important. After which it can be quenched in water and fractured. If it is quenched from higher temperature, okay. If it is quenched from higher temperatures, then martensite will form and you will not get the correct assessment of melt quality. The width at the point where clear chill ceases is measured, and this gives a good indication of the need for inoculation and that of the effectiveness of the inoculation process. In general, casting sections should not be less than 3 times the wedge reading if the chill at the edges and thin sections is to be avoided. I think I have to move a bit faster. This is a picture of actual fractured wedge, and it shows clear chill and mottled zone. And here is a picture taken out of a paper where they were comparing effectiveness of various types of inoculants for reducing the chilling tendency. I mean, the pictures are self-explanatory. So you can either compare the effectiveness inoculants or whether you are using adequate quantity of inoculant or not. Cooling curve and its analysis. The cooling curves are used in 2 ways. When you use cups which are with tellurium coating so that iron freezes as cementite, we use it for your C cups, while uncoated cups will be used for looking at really how the phase transformations are happening. The important point here, I'll not go into too much of depth because I think I have already taken a lot of time. The thermal analysis samples must be taken just before pouring commences to get a true picture of the melt condition. That's the point I'm making. Because if there is a lot of gap before the metal is actually poured, then the condition of the melt will change and you will not get the correct microstructure. Few typical types of castings. For example, for lathe beds, you will use grade 100 iron. For ingot molds, counterweights, 100 to 150. For drain covers, pulleys, 150 grade. For boilers, cooking utensils, walls, 150 to 200 grade. And then, bearing caps and bearing housing and brake cylinders, and this whole list, 200 grade irons. And then for air-cooled cylinders, agricultural machineries, 200 to 50 grade, diesel engine blocks and heads, hydraulic pumps. I have shown pictures of some of them here. We will go for higher grade irons. So, thank you. That's the end of my presentation.